I'll go through the problem statement. We have a boat. It's held stationary by a cable, so there's the boat and cable. We have a fire hose. Okay, I see that also. And it's directing water. The water's going 50 meters per second. Wow, that's over 100 miles an hour. And the allowable load on the cable, so that's right there, is 5,000 newtons. So that's about 1,000 pounds force. And the goal is the mass flow rate and the diameter of the water jet. I'll connect this to what I already know. If I fill up a balloon, shown here, and let it go, the balloon's going to fly through the air. And in order to keep the balloon from flying through the air, I have to put a force on it. And that would look like this. And so right here I have a jet of water coming out, and it's coming out very, very fast. And that would cause the boat to take off that way. But the cable right here is preventing the boat from moving. And so this is like a jet boat or something, and the cable has to hold it stationary. When I think of forces in fluid jets, like on this problem, I immediately think of the momentum equation. And the momentum equation says that forces are balanced by momentum flows, and each momentum flow is m dot times the velocity vector. And I believe I can analyze this problem using the momentum equation. So I capture the problem information, mostly in my situation diagram, and later on in the problem when I needed properties, I wrote them down right here. I left myself a little space, and so I use this property later in my calculations. Here's how I captured the goals. To analyze the problem, I selected the momentum equation, and then I drew a force diagram here and a momentum diagram here, and this shows me visually how the momentum equation is satisfied, so I can see what's going on. Let me walk you through how to do the force diagram and momentum diagram for this problem. So I select the boat as my system, and I decide to represent this using the control volume shown here, so I define my control volume. Then to do the force diagram, step one is I draw the body force. So the body force is the weight, and that'll act through the center of gravity. So I'll use the center of gravity symbol and draw the weight on it. So I draw all the body forces. And then I draw all the surface forces. And the surface forces require physical contact. So I look at the boundary of my control volume, i.e. the control surfaces, and ask the question, what was touching? So down on this boundary, the water was touching, and when I draw my force diagram, the water is no longer present. So I represent the force of the water with an upward force here, which I label as the buoyant force. And similarly, the control volume cuts right here, and I'm going to now represent the force of the cable with a tension force. And so last thing I do is I check and see, did I miss any surface forces? So I walk around the control surface, so I imagine just going around here and saying, what's touching? Well, there's air out here putting a pressure force on, but that's at atmospheric pressure, which is 0 gauge, so I never include that. And as I walk all the way around the control volume, I see that I've gotten all the surface forces. So my force diagram will show the buoyant force, it'll show the weight force here, and it'll show the tension. We'll come back and look at that in a second. But that's the basic thinking I use. Oh, and I forgot one thing when I did my force analysis. This jet is also coming across the control surface right there. But the key idea is, in a free liquid jet, such as this one, the pressure is everywhere at ambient pressure, which is 0 gauge. So there's no force here. To do my momentum diagram, all I do is I look at the control surface and I say, where's there mass flow across the surface? And the only place there's mass flow across the surface is right there. And what I do right there is I simply draw a vector and label it m dot v to show the momentum flow going across the control surface. And if there were inflows, I would draw arrows to represent those, but there's no inflows on this problem. So on my force diagram right here, I see the three forces, the buoyant force, the weight, and the tension of the cable, and I see the outward momentum flow like this. Here I've written the general form of the momentum equation, and the sum of forces physically represents these three forces that I've shown up here. So here, here, and here. The accumulation of momentum, this term, is 0 on this problem. The simple explanation is if the control volume is stationary, this term will basically always go to 0. The momentum outflow term, this one right here, is represented by this vector, and there's no momentum coming in, so I can drop that term. And of course, the easy way to do the momentum equation is just take the vector terms right off the pictures. And so I'm going to sum forces in the horizontal direction. This little cartoon shows my direction. And so I look at my force diagram, and the only force which has a component in that direction is T. And positive is to the right, so I write down the forces. So this is the only force right here. And then on the momentum flow diagram, there's only one momentum flow, and it's outflow, and so it's positive. And so the x component of it is the magnitude m dot v, and then if I use cosine of 60, I pick up the horizontal component. So there's that term. So the momentum equation simplifies to t is equal to m dot v cosine 60. Next, I do my term-by-term analysis shown here, and this reveals I have only one unknown, so I can solve this equation for m dot and find my first problem goal. And my second problem goal was to find the diameter of the jet, so I need to use a new equation for that. So here's my thinking. Mass flow rate can be found, and my new goal is d. And if I think about it, m dot is equal to rho AV, and A has diameter in it. I can use the flow rate equation to solve for my new goal. So here's the analysis. I select the flow rate equation. I write down the form I'm going to use. I substitute for area, pi d squared over 4, and I do term-by-term analysis. I consider m dot as known because I already know how I'm going to calculate it, and I can see from this that I can easily calculate d. So I make my plan. I can solve for mass flow rate using the momentum equation, and I can solve for diameter using the flow rate equation. Apply the momentum equation. I rewrite the equation that I derived in my ideas section. Carry and cancel units as usual, and the mass flow rate is 200 kilograms per second. To apply the flow rate equation, I rewrite the equation I derived in the previous section and solve for diameter. I substitute numbers in, carry and cancel units, and the diameter comes out to be 7.14 centimeters. In review, when I have a fluid jet, I solve the problem typically by balancing forces with momentum flows. And on this particular problem, I only had an outward momentum flow, and there was no incoming momentum flow. So it's a fairly straightforward problem. The key to doing momentum problems is to visualize the physics with a force diagram and momentum diagram. From these diagrams, you can directly write your equations and then solve the problem. I hope you've enjoyed the video, and I hope you found it very useful. We'll see you next time.